Good morning. Yesterday we were discussing about dynamic shared memory, and in that class we also had a question that if you have multiple arrays, how can we decide how to access those multiple arrays, because we are not allowed to specify the size of that array here. And we guessed that it might be the case that you specify the overall size requirement here, and which is required for multiple arrays, and then you declare a single variable which is for the shared memory, and have multiple such pointers which are going to then point to appropriate locations in this array, which signify internally multiple arrays. So that turns out to be true, and the rest of the code kind of remains the same as if you have declared S1 and S2 as in shared memory, just that their array sizes are coming at runtime. Those are not known at compile time. Then there was a second question, which was like, if you have these two types of, or these multiple types to be of the same type, then it might be okay. But if you have different types like char and int and let's say double and then some structure, etc., doesn't that create some sort of padding issues? And my guess was that it doesn't on GPU, but it turns out that yes, it will create the padding issues also on the GPU, and therefore it's kind of programmer's responsibility to somehow take care of it. So you need to figure out that it's aligned at, let's say, 32-bit boundary, and therefore if there are, let's say, 3 characters followed by 1 integer, then that is like there will be padding of 1 particular byte just before the integers start, and so on. So this is something which we as a programmer have to take care of. Alternative, of course, is that you can go for a static shared memory, in which case you become a little conservative in terms of the memory requirement, but you avoid these problems altogether. All right. So any questions on this dynamic memory part? All righty. We'll move ahead from here. We were looking at some overall aspects of the GPU. We discussed about, let's say, the requirement or motivation for having parallel system, right? Where we talked about the clock frequency is getting saturated, but the number of transistors that you can pack in, that is going on increasing, and therefore the only way we can make use of these additional hardware or additional resources is by going parallel. Then we also looked at different graphics kind of processors which have evolved over time. Initially those were graphics processors, then we made the shader programmable, so it became graphics processing unit, and then we further added other libraries and capabilities in CUDA, which made it more general purpose, and therefore it became GPU. So this trend also we looked at. The other aspect that is important, which keeps coming back once in a while, is the compute capability. What this indicates is whatever are the different capabilities of the hardware, that is signified by this compute capability. This is specified using some sort of versioning, similar to our other many of the software that we have, in terms of some major number and some minor number. For example, you can have it something like 6.2 as a compute capability. So it has so happened that CUDA has evolved, or not CUDA has evolved, but GPUs have evolved over time, and therefore the newer GPUs might have certain functionality which might not be there in the previous one. However, since this development has been happening very fast, it's possible that you might have an older GPU, but you might have a newer version of the software. I mean, you might have a newer CUDA libraries installed, but you are working with an older hardware, in which case the hardware is capable of performing only certain type of computations. It does not have certain features, which at the language level, at the CUDA library level, you might still be able to support. In such cases, it is important to compile your code with respect to the previous compute capability, whichever is supported by the hardware. And that is specified when you inform the compiler that this particular GPU for which I am compiling, it supports a compute capability of, let's say, 6.2, and that can be specified using -arc equal to SM_62, and there are other ways in which that can be specified too. So this way, then the compiler knows that it is able to compile for a particular older GPU or newer GPU or newest GPU and so on. There is also a macro in case you want your code to be made portable across different GPUs. You can use something like this. Sometimes you can make the same code run on the CPU as well as GPU, as we saw in the linked list example, and we are going to study it further soon. So this macro cudaArc is defined only in the GPU code, right? So if you have some sort of CPU code, you can just check if def cudaArc, and if that is not defined, that means you are working in the CPU part, and if that is defined, that means you are in the GPU part. And its value could be some positive number, a major number followed by minor number followed by 0 in the device code. Right? So this way, by adding #ifdefs using cudaArc, you will be able to even write different kinds of codes if you are compiling for different architectures, so to say. The CUDA version that we usually talk about, for example, there was a discussion that I installed these libraries and there was sudo permission issue and so on. So that is the software version. That is not the hardware part. Right? So the although CUDA architecture has involves different capabilities of the hardware, but it is primarily dealing with the software version as far as the libraries that we install, etc. And this definitely has more capabilities than a particular hardware for which you are generating the code, because it needs to adhere to multiple capabilities of the different GPUs across different versions. So therefore, you are able to specify this -arc command such that you can compile for a particular GPU version. Okay, so there are large number of such compute capabilities which have gone across different versions, and especially this major number is the one which defines a different family of GPUs, right? So I'm just going to show you the first two. For example, we had the Tesla GPUs and the Fermi GPUs, right? So that's the architecture which is defining. It's some sense processor family, right? So there will be multiple such GPUs in a particular family. So if the major number was 1, those were Tesla GPUs. There are Tesla GPUs even now. So those are based on this particular type of architecture. That doesn't mean that those are old. Those could be new also. It's just that the original name that was given to Tesla architecture GPUs was, family of GPUs was major number 1. Then came Fermi, which was the major, which had major number as 2. What is the next one?
Pascal.
Okay, good guess. Any other suggestion? Maxwell, okay. That's also a good guess. Volta, okay. Good. So you know some okay. So you know these terms. That's good. That also shows that the kind of GPUs which are there existing today, those are not really. I mean, those are the ones that you guys have suggested: Pascal, Maxwell, Volta, Turing. These are the relatively recent generation GPUs. The compute capability 3 is little older, right? So all these Volta, for example, will be able to talk about some sort of compute capability of 7 point something, etc. So we are still talking about 3. So let's see what that is. So that used to be called as Kepler, right? What is the next one? Any suggestions? Okay, now one of these answers might match, but interestingly, the compute capability 4 is missing, right? So it went directly to 5, and that was Maxwell. And now the other answers will most probably match. So 6 is going to be Pascal, and 7 is Volta. And then there is another answer which is Turing here, and that is compute capability 8. So Volta is still getting used. I mean, there are other, I mean, even Kepler gets used by some people. Pascal is also around, Volta is also around. Turing has started catching up now, but there is further beyond Turing. Anybody knows what is the most latest one? Okay, Ampere. Okay, good. So that is compute capability 9, which is the Ampere. So this A100 GPUs are currently the latest ones, which seem to be quite powerful. Does that mean that this is the end of the story so far? Well, so far, yes, it is the end of the story. But there are things that are planned for future. So their major numbers are anyway 10 and 11, but their architecture names are also specified, although those are not yet in the market. Anybody by chance knows the names? Okay. The hint is that, I mean, this is my guess that it's probably going to be something to maybe encourage the, let's say, women in computing. Or let's say scientists in, female scientists. Curie, Ada, Lovelace. Okay. Okay, that's good. Right. So yeah, in some sense, yes. So the 10 is codenamed as Lovelace, and there is 11 which is codenamed for Hopper. All right. So this is just as an aside, but definitely something which, as a general knowledge around GPUs, you should be definitely aware. Okay. So as we increase the different capabilities of the GPUs, there are new features that keep getting added. For example, in 2.x, we had the support of atomics, which was not there in 1.x, for example. This is compute capability, major number and minor number I'm talking about. Then there were warp voting functions. These also we are going to study towards the end of the course, where across the threads within a warp, you could perform some sort of voting. Let's say you can perform how many threads within a warp want to say yes and how many want to say no. Right? So this voting you can do quickly. I mean, you can always simulate it, but this is supported in the hardware. So that warp voting functions turns out to be an interesting functionality sometimes. Then this sync threads, that is the block level barrier, was not there earlier, which got supported in 2.x. Then in 3.x, we had the notion of unified memory. Then unified memory essentially means that you have the capability of accessing the same memory location from both CPU and GPU. This is also something which we are going to study in the future classes. So that was one. Then the dynamic parallelism, which is about what? Dynamic parallelism is about what? We briefly discussed this some time back. So, okay, calling one kernel within another. Good. Yes. So this is about the nested kernels, and that is dynamic parallelism, which got introduced in Kepler, and that turned out to be quite an interesting phenomenon for some of the codes, considering that in many natural phenomena we have this nested for loops, and that could be nicely translated into these nested kernels. So there was a requirement, and which got fulfilled because of this dynamic parallelism at the language level. However, there are limitations of this dynamic parallelism when it comes to the amount of parallelism that you can exploit. So it's not really that if you have n cross n number of threads, so each of the n threads is forking n of the threads in the kernel, that doesn't mean that you really get n cross n amount of parallelism. There are limitations to that. It has something to do with the number of thread blocks, but we'll study that too later. Note that it so happens that all of these functionalities seem to be backwards compatible, which means that a particular newer version contains all of the facilities of the previous version. Until then, we had support for atomics only for the 4-byte data types, that is integer and float. But there was, I mean, as the data sizes were growing, as well as people started making use of GPUs for many different applications where double precision turns out to be a very important aspect. Therefore, the atomics for double was not present earlier in the earlier GPUs. So those used to get simulated. So there is a mechanism using which you can simulate atomic instructions for 2-word data type, that is for 8 bytes, that is 64-bit data type, using single word data type. So that was what people used to do, but which was painfully slow. And therefore, when it was supported in the hardware, that really added a good boost to many of the applications, because we need to maintain that precision in many of these weather forecasting, molecular dynamics, as well as our mechanical engineering, aerodynamics kind of applications. The next part came, which is quite relevant today, is the tensor cores, which were introduced in Volta. So you can perform certain tensor computation, small matrix computation in the hardware itself, and that got supported in Volta. And in fact, the lot of marketing of Volta happened based on these tensor cores because of the machine learning, deep learning related work being in the limelight in the recent past. Then there is something called as hardware asynchronous copy. Earlier, this used to be supported more like a library, but now there is a possibility that you can make use of, I mean, the hardware is going to accelerate this asynchronous copy. So that got supported in the latest generations in the Turing architecture. And there will be more as we go along. But this is just to give you some glance of how things evolved over time. All right. Any questions so far?
Sir, can you elaborate a little bit on the hardware async copy? Like, I'm not sure what do we mean by the hardware part for the async copy.
Okay. So what is the meaning of hardware accelerated asynchronous copy? Yeah, actually, I also don't know exactly what that means. Okay, let's put it this way, that our usual cudaMemcopy that we talk about, that is happening on the PCI Express bus, right? And that PCI Express bus can get used in both the directions. In the sense that you can copy from CPU to GPU as well as GPU to CPU at the same time. However, this needs to be completely modeled in the program, right? That is in your software. What my guess this hardware acceleration is that the hardware is going to take care of if there are simultaneous copying happening in both the directions, then it will try to do it automatically itself rather than a programmer requiring it. Right? So that is my guess what will happen, but I can confirm this. I think I'll check this out and I'll let you know.
Okay, sir. Thank you.
Any other questions? All right. So then let's do a little bit of classwork. So this is going to introduce us to some concepts that we will require in future, as well as some concepts that we have learned so far. So the idea is that we want to have some data type like point, which is going to have x and y coordinates, and we have an array n of those values. N could be an arbitrarily large variable, but you can assume it to be a constant. then each thread is operating on 4 elements, right? And that probably means that there are n by 4 threads. We need to find out the average of the x values, all the x values, right? So, and if a thread sees y value above the average of these 4 x elements that a thread is operating on, then it replaces all these y values, these 4 threads, I mean that thread which is operating on these 4 elements, with the average of these x values. Otherwise, it adds y values to a global sum, right? And then finally, the host prints the number of elements which are set to the average value. So there are n elements which are being operated by n by 4, and the number of elements which are set to, let's say, this some sort of average, those number of elements we need to print in the host. So we have to maintain that counter in some sense in the kernel across all threads, right? So please think about it, and if you have questions, please ask, and please start working on this particular classwork. If it helps, initially you can assume that n is let's say maximum 4k or something, which means that with 1024 threads, that is within a single thread block, you will be able to operate on all of these, right? And then you can try extrapolating it for more number of values in case it helps. Otherwise, you can directly work with the larger, more number of threads, more number of values of n. Anybody facing any trouble, any questions, any issues? Okay. So let's first get the first part correct. How do I copy this particular structure? Let's say it's available in CPU somehow, right? So I define it this way, and it's that ARR is available with me. Now there is DARR or some other GPU ARR, and I want to copy all of this into that variable so that it's available in the GPU memory. How do I do that? So how is the allocation of memory and how is the copying on the from CPU to GPU? Can somebody just post that? cudaMemcopy to symbol. That was for the constant memory, Kushal. Here we would like to change the values of x and y. If not x, at least the y. Therefore, we will use the usual cudaMemcopy for this. Yeah, how do you do the cudamalloc in this case? Anyone? Okay, cudamalloc ampersand gpuarray n into size of struct point. Yes, so that seems to be the correct way to allocate memory for the GPU array. Now we want to copy the CPU array, which is, let's say, populated somehow, uh, and that we want to copy into the GPU array. So I hope everybody has gotten what Kushal and Sumit have mentioned.
Sir,
And yeah,
sir,
Venkat.
sorry to interrupt. Sir, what does the size of operator return? Like, does it ignore the padding and just give the X and Y size?
No, it includes the padding also.
So when we do n into size of, I don't get the sense of it because we're just assuming that all the individual cells will be of the same size.
Those will be of the same size.
But like, what if there are alignment issues and in between we have an extra padding and the size of a particular cell goes like it's different?
No, so if there is a padding, that will be added to the structure itself.
So
So
when I'm doing the size of, won't it return more size than?
it can return more size than the individual element sizes. So if
But
I have
will it be uniform across all the cells?
that is yeah, at least I have not seen it to be non-uniform. But yeah, I have seen it to be uniform because the structure is going to get aligned at the particular boundary, and then that structure going to get repeated.
Oh, okay. Fine. Got it. Thank you, sir.
Um Yeah, and this part, this specifically that Venkat was talking about the padding, that is there not only in the GPU but also on the CPU. So the same issues are going to arise there, and I think all our programs work with the assumption that the size of is going to take care of this padding, and then we are going to allocate memory. So even using malloc, for example. Okay, so anybody has any questions to what Kushal and Sumit have written in terms of how to allocate that memory? So by the way, Sumit, this will not be ARR because ARR we have defined as the CPU variable. Yeah, this will be some sort of another variable. That's all. Okay, so now how do we copy the memory from CPU to GPU? Okay, Kushal says cudaMemcopy % of ARR GPU array cudaMemcopy device to host. Okay, yeah. So Kushal, it will be the opposite as Aditya has written. It will be from ampersand of GPU array, comma ampersand of ARR, and cudaMemcopy host to device. And this size of n into size of point also needs to be added. So good. Okay, so that seems to be a good way of copying the memory, copying the whole structure onto the GPU, the array of structures onto the GPU. Now we have it available. Now let's get into the computation. Now we want that each thread is operating on 4 elements. So how should the kernel call look like? Can somebody tell me how the kernel call will be? Again, all of this discussion, all of this classwork is to somehow make sure that you are in sync with whatever we have been discussing. So please spend time on that because otherwise it becomes a little difficult to spend time beyond the class hour. And those of you who are by any chance, or your friends who are missing the lecture, please be alert that somehow the number of lectures suddenly pile up, that too across courses. And we always feel that, okay, I'll go and look up the lecture, I can fast forward it and so on. But it always creates a problem. So it's probably very easy to just be in the class, even if you are half asleep, but at least some things will go into your mind and it will help. Okay, so there is kernel 1 comma n by 4 GPU array. Okay, kernel 1 comma n plus 3 by 4 D array. Okay, so good. So that will take care of the number of threads, and here we are assuming that there is a single block, which means that n is within 4k. So that seems to be good, and Aditya's solution will also take care of any sealing, etc., that is happening because of the number of elements. Okay, good. So now we have launched the kernel. Now inside the kernel, each thread is operating on 4 elements, right? So that is our first part. How should that be written, in the sense that, okay, I'll leave it at that. So essentially we will have a for loop which goes over I equal to 0, I less than 4, I plus plus, and that means that something is going to get accessed by a particular thread ID. Now how should GPU array of something be written using the thread ID as well as using I? So how will that look like? Venkat says I equal to 4 into thread ID x dot x by 4 plus thread ID x mod 4. Okay. It would be sequential using for loop. Yes, Kushal, that is correct. J equal to 0, j less than 4, j plus plus. Aditya says start ID is 4 into thread ID, end ID is 4 into start ID plus 3, and then I equal to start ID is then equal to end ID I plus plus. Okay, so what Aditya has written seems to be fine.
Sir, what I meant was after the int calculation of int I, my for loop is going over j equal to 0, j less than 4, and I'll access array of I plus j.
I see. Okay. So you are calculating the index
Beginning
initially
index.
and then going. Okay, that is also fine. Okay, so I hope people are able to understand this discussion. In case there are any questions, please feel free to ask. For example, you have n by 4 threads here, right? And therefore, your thread ID is going to work on a consecutive chunk of elements and 4 elements. So therefore, the thread number 0 is going to start from 0th, that is GPU array of 0. Thread number 1 is going to start at GPU array of 4. Thread number 2 at GPU array of 8, and so on. And therefore, thread ID into 4 is going to give you starting in. Okay, I hope. Okay, Sumit has written probably a larger piece of code. Okay, Right. So we have this end index to be, let's say, start index plus. You can as well write it start index plus number of elements, and then you can write I less than that ending index. That is also okay. So okay, we'll come to Sumit's code now. We have so we are there with the for loop. Now let's see what happens in the next part. Right? So we want to find the average of these 4 values. Right? So the average, which is initialized to 0, average underscore x in Sumit's code, that average plus equal to gpuarray of I. Yeah, we'll have to divide it by 4 at the end of the loop. Right? So we are finding that sum of gpuarray of I, and then we'll divide it by 4. So that gives you the average of these x values, and it should be gpuarray of I dot x. So that is okay. And then the thread sees the y value above that average. What that means is that the average computation of x must be over by the time you start looking at the y values. Thankfully, we are talking about the x values in the same thread. We are talking about the 4x values for which we are computing the average in the same thread, and therefore we don't need to add a barrier. If this average would have been average of all x values within the thread block, then we would require sync threads here. Right? So that is what was the purpose, and we'll do some modification of this kind of processing, finding average, etc., in later class. But yeah, just remember this part, that will require sync threads as soon as you want to go beyond a what. Okay, so let's assume that average of x contains the average of those 4 elements. After that, we again go from start to end, and then gpuarray of I dot y, if it is greater than average of x, then we set all these 4 values with the average. So gpuarray of I dot y equal to average of x. That seems to be correct. Otherwise, it adds y to the global sum, right? Which means that the global sum is getting added with gpuarray of I dot y. And somewhere we also need to count the number of elements which are set to average. So in this case, I haven't mentioned which element, whether it is x or y, but we can assume that, let's say, it is x or something. So that also code will have to add. So thanks, Sumit, for this. Okay, the voice is audible now. Okay, okay, good. Yeah, I had lost connection for a few seconds in between. So at that time, there was probably no voice. Is it better to access the ID plus 32 into 2, ID plus 32 into 3? I didn't understand. Arihant, are you talking in terms of coalescing or something? Okay, so from the coalescing perspective, you are right that strided access by different threads is going to be reducing the coalescing. That means we are giving a consecutive chunk to each thread. Ideally, it should be that thread 0 is accessing something within a 32 chunk, and then thread the next element that thread 0 is accessing is in the 32nd element, right? So the consecutive elements should be accessed by the consecutive threads within a warp. That is correct. So if you do it that way, that will be better. But it will not be. Will it be ID plus 32? Yeah, that seems to be fine. Yeah, ID plus 32, then ID plus 64, and so on. That seems to be correct. Yeah, so if you want coalesced memory accesses, we need to change the data representation. So the data that we have currently, we are assuming that it is accessing the consecutive 4 elements, which, I mean, there is some computation which we are doing with respect to these 4 elements. If a thread can access any 4 elements, then we just change the access pattern and we are still okay. But in this particular case, since we are finding the average and changing the y values based on this average, we'll have to change the data representation also. That means that we'll have to move the data from 0th element remains there, first element goes to 32, second element goes to 64, and so on. This change we will have to do programmatically. So that seems to be fine. Yeah, Mohit is asking, addition to global sum should be atomic. That is correct. We will not be able to have a global sum plus equal to as a kind of code, because that is going to create data race. The same variable is getting read as well as written to, right, simultaneously by multiple threads, and therefore there is a data race and we need to be careful about that. So that we'll have to worry about. So some sort of synchronization we might require there. Rahul is asking, will there be any difference in performance between SO and AOS while accessing shared memory? When you have structure of arrays versus array of structures, will there be an issue in the shared memory? A little bit, but not because of coalescing. It will be because of the banks conflict rather than coalescing, because the coalescing comes into play when you are accessing it from the global memory. So within the shared memory, since that is still an L1 cache, only the bank conflict comes into picture. The coalescing will not come into picture. So AOS and SOA will matter from that perspective. Okay, any other questions here? Okay, so that means that we require some sort of synchronization when we try to add values here, but there is another synchronization required somewhere else. Where is that?
While finding the number of elements set to average.
Yes. While finding the number of elements set to average. No, not while finding.
Like while adding all the across the threads.
Yes, while counting the number of elements set to average. That is correct. So we are going to look for, let's say, the values of x. If that is same as the average, then we are going to increment a counter. This increment a counter is very similar to adding to global sum. Global sum plus equal to blah versus counter plus equal to 1. Right? So both of these are relative updates in the sense that there is reading of the value as well as writing, and that is happening simultaneously by multiple threads. So there is data race in both of these aspects. So this also is going to require some sort of synchronization. Again, currently we have not studied what kind of atomic and what kind of synchronization we should do, but you should be able to identify that there is a data race at this stage. Okay. So any questions on this one? It might be worth trying it out. I think most of the code is given by many of you, different parts, and Sumit has written almost all the code. So it might be worth just improvising on that code and see if you are able to get this code working. Okay, if there are any questions, we can take those up now. Okay, so then that kind of is bringing us to the end of our discussion on memory related aspect. I'm just going to spend, let's say, 5 minutes on giving you a brief overview of what all happens on in the CUDA. And if there are any questions, we can take those up now, so that this will form our basis for going further, which is probably going to be a little more interesting and little more complicated too. Right? So CUDA is not only a language, it's called as architecture, which involves both the software as well as the hardware components of it. And that defines not only, let's say, how you should allocate memory, and when you allocate memory, where it gets allocated and whether it is accessible from CPU and so on. Not only that part, but also that when you have some sort of synchronization, how do you deal with, what are the guarantees that are given when you have those synchronizations, right? So we said, for instance, that when you have sync threads, then that ensures that there is no thread executes the next instruction before completing the previous instruction within a thread block. But what does it mean when you are talking about, let's say, there is some memory location which I have modified, and there is some other thread which is reading from that memory location. Does a barrier affect this particular aspect? Or when later we will talk about atomic instructions, which part is accessible to other threads? Because each thread has its own local cache. There was a question when we were discussing about this, that does the consistency and coherency come into play here? Yes, it does come into play, and that needs to be specified by this architectural design. So CUDA, it works only with NVIDIA GPUs. It's a proprietary kind of piece of software which is written which allows programs to be written in all these different languages, C, C++, Fortran, OpenCL, and a few more. Some of these are also in research works. There are people who have developed, for example, Python interfaces where you can write your code almost in Python and then copy it or compile it and run it on the GPU. You can as well write something, let's say in MATLAB, and using some connector, you will be able to run that code in MATLAB for on the GPU, for example. A CUDA program that is from main, you can call something called as parallel kernels, and kernel executes across a set of parallel threads. The programmer or the compiler, sometimes the compiler can also organize depending upon so, I mean, the programmer tells how many threads need to be there in a thread block and how many thread blocks, but how those get managed, that is actually at runtime, the compiler doesn't play a role. But the compiler is going to create assembly instructions which are understood by the GPU at runtime to make sure that those many threads run in terms of the blocks and the grids that we are aware of. Then the GPU instantiates at runtime this particular kernel program using a grid of those parallel thread blocks. And it also distributes these thread blocks across different streaming multiprocessors so that there is some sort of load balancing done. But if you run the same kernel onto one GPU, the number of thread blocks that might get assigned to the streaming multiprocessor might differ across GPUs. And that's because the number of SMs might differ across GPUs, the number of cores which might be available within an SM might differ, and so on. So based on the hardware capabilities, the GPU driver at runtime will decide how the thread block distribution should be. And therefore, it is expected, that was the original thought process in mind, that the thread block should be independent of each other. So the thread blocks should be independent of each other. There is synchronization provided within a thread block. There is synchronization automatically there within a war. But as far as across thread blocks are concerned, those should be independent of each other. You should be able to run them arbitrarily. Right? So that was the thought process. Of course, we'll break this as we go along because we are dealing with probably codes which will require synchronization across thread blocks. So each thread within a thread block executes an instance of the kernel, has its own thread ID, which might be in a 3D space. It has its own program counter, which means that different threads might be executing different instructions. It has its own set of registers to keep track of some of the temporaries. It has per thread private memory, which is also allocated sometimes from the register, sometimes from the local memory. And then it has its own input, that is the arguments that you pass, and output results. This essentially means that if you are writing to some local variable, then it is going to produce that output. But otherwise, thread really doesn't return anything. Right? But as far as GPU is concerned, it must be keeping track of some sort of metadata with respect to each thread also, which is not really accessible to us. A thread block is a set of concurrently executing threads that can cooperate. And this is an important point, that we are having this shared memory as well as sync threads, which is defined for a thread block. There is no such thing for across thread blocks. So the cooperation is happening within a thread block, but not across. Right? And we will do that coordination across thread blocks also soon. A grid is an array of thread blocks, right, that execute the same kernel, which read from global memory as well as write to the global memory. Right? So we are talking about different thread blocks, which the only common memory across all of these is going to be global memory, which is accessible to the programmer. There is also L2 cache, which is available, but that is not something which is accessible to the programmer. Each thread has a private memory space. This is similar to the earlier one, which can be used for register spills. So whenever you require more registers per thread, then you use those registers, and then it spills to a private memory space. But by default, it gets mapped to the global memory, and therefore the register spills are considered to be very costly, which can also be used for recursive function calls, as well as the local variables which are defined on the stack. And each thread block has a per block shared memory. This we talked about.
Sir, hello, sir, am I audible?
Talking about, sorry, any
Sir?
questions? Yeah, go ahead.
Am I audible? Sir,
Yeah,
when we're talking about the private memory space, we are talking on the global memory, and we are talking about the stack or something that
yes,
each
yes,
thread maintains.
yes. So that
Okay.
stack is also part of the global memory. So if there is registers available, some of those variables will get mapped to the registers, and the rest of it will get mapped to the global memory. There is one small difference between that. The local memory also gets coalesced, which means that if you define some variable onto the stack, let's say x, and that is getting spilled, that x is getting defined across all the threads of the warp, as well as thread block, as well as the GPU. So the these different access from different threads within the warp, these also get stored consecutively, so that the warp accesses to X are going to get coalesced.
Okay, sir.
Yeah. Any other questions? All right. So that completes our discussion on memory. From our next class, we'll start discussing about synchronization. If you have any questions with respect to any part of the GPU programming that we have done so far, and if you want to have Friday as a doubt session for your own benefit, please let me know by email or post it on Moodle. We can convert the lecture to doubt session if at all you require. Otherwise, if there are no mails like that, or not many emails like that, then I'm going to just start with the synchronization part. All right, see you.